so loud. But again, today's topic is Euclidean geometry. We're going to start with the 3 undefined terms of Euclidean geometry. So these terms are called undefined terms because they cannot be measured. And they are point, line, and plane. So those are our 3 undefined words, our undefined terms, in geometry. And then from there, I'm just going to go over some symbols that I hope that we're familiar with. Sometimes you'll see this symbol, or you'll see it like this. And this is referring to an angle. Whenever you see this little symbol on top of some letters, that is a line. So a line is never ending, which is one of the undefined terms. It can't be measured. Then we have like this symbol, that is a ray. And then we have this symbol, that's a line segment. When you see this in front of an angle sign, that means they want the measure of whatever angle they're talking about. So those are a couple of basics. I'm running through some topics, so if I pause a little bit, sorry about that. I'm just trying to decide which topic I want to go to next. So let me draw a line. I'm going to put 2 points on it. I'm going to name them A and B. So this line is never ending. It's going forever and ever in both directions. And I'm going to name a couple things and tell you the difference between them. So let's say we have this. And we have this. And we have this. And we have this. So these are all like using the same letters, but they're all different things. This means line AB. This means ray AB. This one is ray BA, which means just the ray going in the opposite direction. And this is line segment AB. So let me highlight those different ones. So if we're talking about line AB, we're talking about the whole thing forever and ever, extending in both directions and never stopping. If I want ray AB, that's going to start at A and then go in the B direction forever and ever that way. Ray BA is going to start at B and go this way forever and ever. I should have used a different color for that. Let me switch it. This way forever and ever. And then line segment AB is just this middle part. So those are the differences in the symbols when you're talking about rays, lines, and line segments. So let's do an example with some numbers. So let's say we have this line with A here, B here, and M here. So we're gonna say suppose M is the midpoint of AB. So a midpoint is the middle. It cuts a line segment into equal pieces. So if M is the midpoint, this means that AM is congruent to AB. Okay, line segment AM, not AB. MB. Sorry about that. Okay, so if AM is equal to 2x plus 1 and MB is equal to 3x minus 3, solve for AM, AB, and MB. So we're going to use these expressions to solve for the missing parts. The unknown parts. So let's label our picture. AM is 2x plus 1. MB is 3x minus 3. So from here, we need to figure out what is the relationship between this expression and this expression. The midpoint formula tells us that this side is equal to this side if we know M is the midpoint. So since they're equal, we can simply equal them to each other and algebraically solve for x. So I will distribute, and I get 2x plus 2. Distribute over here, and from there we'll just do some algebra. And x equals 11. Now that's not what they want. They want us to actually solve for these, so we need to plug them back in. So if AM is equal to 2x plus 1, and now we know that x is 11, all we have to do is replace it and solve. Now if you want to plug it in for MB, you can, but since we know that M is the midpoint, MB should also be 24. They should be equal. So let's show that it is equal. 3 times 8, 24. And then we also need to find AB. So AB would just be 24 plus 24, which is 48. Now this is part of the segment addition postulate. And the segment addition postulate basically just says that if you have a segment divided into two pieces, the whole segment is equal to the sum of each piece. So in this case, AB is equal to AM plus MB. And you could have more than one section, like you could have, or two sections, you could have a line broken up into three pieces. And so the segment addition postulate would tell us that all three pieces are equal to that one piece. So let's look at another example. Let's work this one again. But this time we're going to suppose that M is not the midpoint of the line segment. We want to solve for x. And let's say we know AM is still 2x plus 1. MB is still 3x minus 3. But now we also know that AB is equal to, let's make it equal to 8. Okay, and I think that should work out nicely. So in this case, if M is not the midpoint, we can't set those equal to each other. We can't set AM equal to MB. But because of the segment addition postulate, we can actually set up an equation to solve for x. This is our total, so we're going to add 2x plus 1 plus 3x minus 3 and set it equal to 8. So now we can add it and set it equal to that total. I'm not going to work that one out all the way, but that's the equation that we would use to solve for that. Okay, let's move on and talk a little bit about angles. So angles also have an angle addition postulate. That is not the pen. So the angle addition postulate is basically the same thing as the line segment, the segment addition postulate. If I have an angle, it looks like this, and let's say this is A, B, C, D. So the angle addition postulate also says that angle ABD plus angle DBC is equal to the angle ABC. Okay, so you can add the small two angles to equal the big angle, which I believe, we all know that, and it's probably common sense, but that's called the angle addition postulate. And let's talk about some different types of angles. We have adjacent angles. We have congruent angles. We have supplementary angles. And we have complementary angles. And there's one more that I'm not going to have room for, so I'm just going to write it up here. Vertical angles. So these are all our types of angles. Again, please remember the material that I'm going over is what you would normally teach a high school geometry class. So I don't think it's too high level, but I think the important thing here is just understanding the content a little bit better and all that. So adjacent angles are angles that share a vertex. That share a vertex and have a common ray. So the example above is actually an example of this one right here. Those are adjacent angles. So angle ABD and angle DBC. Those are adjacent angles because you can see they share this vertex right here, and they have this ray in the middle that they share. So those are adjacent angles. Congruent angles are pretty obvious. They're just angles that measure the same degrees. Supplementary angles add up to 180 degrees. And then complementary angles add up to 90 degrees. Now vertical angles, super important to know, they are congruent. So anytime you have vertical angles, you can always assume that they measure the same thing. And normally you'll see vertical angles. I like to tell the kids that they're angles that are across from each other, which that's not like the mathematical definition of vertical angles, but I think it really helps them picture them. So like if I number these angles 1, 2, 3, 4, so the vertical angles are going to be the ones that are across from each other. So like 1 and 3 would be vertical angles, and then 2 and 4 would be vertical angles. So those angles are going to be congruent. It's not listed here, but we also have linear angles. I'll go ahead and go over linear angles as well. I'll write it right here. Linear angles are sometimes they're also called a linear pair. So either one is fine, but a linear pair, you'll normally see it like this. So angles 1 and 2 are a linear pair. Linear pairs are also supplementary, which means they add up to 180, always. Because they're like a straight line, and there's 180 degrees in a straight line. So if you look back up here at this picture, with the vertical angles, that picture also has linear angles. 1 and 2 are linear, 2 and 3 are linear, 3 and 4 are linear, and 1 and 4 are linear. Okay, let's talk about a bisector next. We're almost finished. I have a couple more things to talk about. Just a bisector. So you can have like an angle bisector. You can have a bisector that bisects a line. But a bisector just splits whatever, whether it's an angle or a segment, it splits into 2 equal pieces. Now, I'll tell the kids, I'll ask them, what do you think bisect means, and a lot of them will be like, well, I don't know. And I'm like, okay, well, let's look at I think that's called the prefix. Sorry, I'm not an English person. I'm like, bi, okay, what does bi mean? And most of them, can tell me, okay, bi means two. So then from there, we're like, okay, well, then bisector just means to cut it into two equal pieces. And so that'll help them kind of remember what bisect means. And I think there's a problem in the homework about an angle bisector. So just know the bisector cuts that angle in half, so it makes those two pieces equal. And so the last thing we're going to go over is the distance formula and the midpoint formula. So your distance formula is the square root of x squared, not x squared, of x minus x squared plus y minus y squared. So when you see it on a formula chart, like once you get into a classroom, like any formula chart, you'll see that the distance formula, they actually have it like this, with the y2 minus y1, but I always show my kids this, because the order doesn't really matter. You're squaring the numbers anyway, so it's going to be a positive. So I like to tell them, like, the order of the x's doesn't matter, the order of the y's doesn't matter. But just be aware that whenever you start teaching on any formula chart in the high school, like the STAR test charts and all that stuff, they're going to show the formula like this. So, you might mention to the kids, like, the order doesn't matter. Talk about why doesn't it matter, show them that, like, you can plug them in one way and plug them in the other way, and, you still get the same answer. And that's a perfect time to talk about, like, commutative properties and all that, and why you get the same answer. So the distance formula, sometimes I like to show them that the distance formula is actually derived from Pythagorean theorem once we get to Pythagorean theorem. So that's also an option, because when they're doing distance, when they learn to do distance like on a coordinate grid, and let's say I have a point here and a point here, and so we're trying to find the distance. Some kids, like, they learned in middle school, I don't know what grade y'all are looking to teach, but like they learned in middle school, hey, let me make this a triangle because I can count the horizontal distance and I can count the vertical distance, exactly. And then I can do Pythagorean theorem to solve for this hypotenuse. And so some kids learn to find distance on a grid that way. And then showing them the distance formula, you can kind of show them, like, hey, that's really the same thing. Like when you're finding the horizontal distance, you're just subtracting the distance of the x's. When you're finding the vertical distance, all you're doing is subtracting the y's, the y coordinates of those points. You're still squaring them and taking the square root, because for Pythagorean theorem, you have to take the square root to undo that c squared. So making those connections will really help their understanding. And then we have the midpoint formula, which is used to find the midpoint between 2 points. And that midpoint formula, x plus x divided by 2, I like to tell them it's like the average. You're finding the average of the x's and the average of the y's. And also on a formula chart, you'll see it with, I think it has the numbers. Like that. I don't know what order they're in. I put them in different orders. But I know it has like x1, y1, x2, y2. And again, mention, the order doesn't matter. We're adding, doesn't matter what order you add it in. But that is the midpoint formula. And I think there's a question on the homework that says something about how you have a circle and you have the diameter and you have the two endpoints and they want to know the center or something like that. So, you really have to, or the kids would really have to understand, like, hey, they're really wanting me to find the midpoint. So in geometry, like, it's not so much knowing how to use the formulas, because I think the kids are smart enough to take numbers and plug them into a formula, but it's like understanding what is a midpoint, what does it do, so that when they get to a problem that says, like, okay, here's the diameter, here are the endpoints of the diameter, what's the center of the circle, they really need to understand, hey, I'm looking for the midpoint. And I think that brings us to the end of the Euclidean geometry unit. Hopefully, I think that covers everything that's on your homework. This is my first time recording using this program that I'm using, so I'm about to see if I can figure out how to stop this without, super easy. See y'all.